18-4. Equilibrium acids, bases, and salts. So, weak acids and bases. Okay, we finally get to this. Now, for any weak acid, okay, you know by definition of weak, it doesn't break up very much. So, it will break up into H plus and A minus. Okay, even though really what happens, don't forget, is it actually reacts with water, H2O liquid, and you're supposed to get H3O plus and A minus. Okay, but when you write out the KEQ for this does not show up in there. So it still basically looks like the same thing. Okay, but don't forget H plus is actually H3O plus. Okay, but since it's in equilibrium, we can write a KEQ for this. It's concentration of the products, H plus and A minus, over HA, which still does appear in there because the molecule is aqueous. Okay? And we now call this a Ka. This is the acid dissociation constant. Okay? Because the amount of acid that actually ionizes is really small in the weak acid. Okay? The equilibrium concentration, this is after it's done ionizing, is pretty much equal to the concentration of the whole molecule. So in other words, if we said it was like 0.10 molar HA, this is the concentration of the HA before you dump it into water and it breaks up. Okay, but the equilibrium concentration is basically the same thing. If you guys were in regular chemistry, we would say that this equilibrium concentration would be equal to the concentration of the acid. Okay, but you guys are in honors, so you have to take into account the amount that breaks up. Okay, and we know that HA, H plus and A minus are small, but because they break up into a 1-to-1 mole ratio, their concentrations will be equal to each other. Okay, so remember, going back to chapter 15 and 16, pH is equal to the negative log of the H plus. H plus concentration is 10 to the negative pH. Plus we also have the pOH equations too. Okay, and pH plus pOH will equal 14. These numbers apply, or this number applies at 25 degrees Celsius, but we'll assume that we're always doing it at 25 degrees Celsius. Okay, and H plus times OH minus is going to give you 1.00 times 10 to the negative 14. Again, this value right here is at 25 degrees Celsius. Okay, now, how to use all this stuff? Okay, how do we find the pH of a 0.1 molar hydrofluoric acid solution? And the Ka for hydrofluoric acid, 7.2 times 10 to the negative 4th. Okay, so first thing, break it up. Okay, we got HF, which is our hydrofluoric acid. You need to know your formulas. Okay, and it's aqueous, so it'll break up into H plus and F minus. Okay, and both of these are aqueous. Okay, so the Ka equation for this is going to be equal to concentration of H plus times the F minus, and we have to include the HF because it's aqueous. Okay, now we'll do some things in terms of X. Okay, so H plus concentration, we'll call that X since we are looking for the pH. That's what you need to solve for. Solve for the H plus. Okay, and we know that H plus concentration has to equal the F minus concentration because we don't know how much H plus you get, but it's a 1-to-1 mole ratio. So they'll be equal to each other. So that will also be equal to X. Okay, now the HF concentration after it's done breaking up. Okay, it's equal to the initial concentration, which is the amount of the acid that was in the solution, minus the amount that breaks up. Okay, now 1 mole gives you 1 mole. So we're creating X. That means you lose X, not 2X, just X, just a 1-to-1 ratio. Okay, so the initial should be equal to 0.100 molar minus the amount that breaks up, which is X. Okay, plug those in, everything into our equation here. We end up with the Ka 7.2 times 10 to the negative 4th is equal to, that's X, X squared over that. 0.100, the initial, minus x. Okay. Now, how do you solve for this? Okay. Well, one way, method one, okay, is cross multiply, solve for, set everything equal to 0, and use the quadratic. Okay, and then that will solve for x. Your x cannot be a negative value because you cannot have a negative concentration. And what happens if the x's are two positive values? X cannot be bigger than 0.10 because when you subtract it from the initial, this concentration can't come out to be a negative value either. So if you do come out with two positive roots, make sure you pick the one that is smaller than the initial concentration. Okay. And that will give you the H plus. Don't forget, you're looking for the pH, so you have to do the negative log of the H plus, which means it's the negative log of the X that you just solved for. Okay, so that's one way to do it. Now, there's a faster way to do it. Okay, you can use a method called successive approximations. Okay, we still go back to the original value, the original numbers, where Ka is 7.2 times 10 to the negative fourth. Okay, and we still have x squared and 0.100 minus x. So 7.2 times 10 to the negative 4 is equal to, we have x squared on the top, and 0.100 minus x. Okay, now what we do is we assume values for the x down there. Okay, and then you solve for the x squared on top. Okay, now, how do you do this, and why can we do this? Well, we're assuming that, remember, this is the amount that breaks up. So we're assuming x is small. Okay, which is why this will actually work. If x were not small, this wouldn't give you a value. So we basically play with a bunch of guesses. And your first guess, we make x equal to 0. Okay, now that's basically what happens if you were in regular chemistry. We would assume that this concentration is so small that the equilibrium and the initial concentrations would be the same. Okay, so for trial number 1, 7.2 times 10 to the negative fourth is equal to the x squared on the top. On the bottom, this bottom x is 0. That's our guess number 1. So it's just going to be 0.100 minus 0. Okay, now, pretty easy to solve. X is going to be equal to the square root of 7.2 times 10 to the negative fourth times 0.100. Right? Cross multiply, that'll give you x squared, take the square root of it. Okay, and solve for that. And you should come out with x is equal to 0.00845. Okay, now this is your guess number 2. Okay, you just solve for x, so guess number 2, x is equal to 0.008485. Okay, so what do? I go back to this original equation again. This is the original. Okay, and then plug in my value for x up in there. Okay, so x becomes equal to the square root of, and the equation is always going to be the same, the Ka 7.2 times 10 to the negative fourth okay, times the initial 0.100 minus x. X was 0 the first time, x is this the second time, 0.008485. Okay, now why is this fast? This number is already in your calculator. Just change it to a minus, add 0.100 to it, push equals, then multiply times that. Okay, and then take the square root of it, and you come out with 0.008117. Okay, now this is going to be my guess for my next trial. Okay, x is going to be equal to 0.008117. Okay, so plug that in again, and calculate new x. This goes back into that equation up there. Okay, so it'll come out to be the square root of the Ka, 7.2 times 10 to the negative 4th, okay, times 0.100 minus x, okay, and this will come out to be 0.008134. Okay, now, when can you stop doing this? Well, when the x values come out to be the same, because if you keep plugging the same x value into the same equation, it'll be exactly the same. But when can I stop? Well, take a look. This has 2 digits in it, which means my sig figs only have to repeat to 2 digits. So basically, this was 0.0085, this was 0.0081, this is 0.0081. So now I can stop. So I can say x is equal to 0.0081 molar. Okay, and that's my H plus concentration. Okay, don't forget, I need to find the pH, so it should be equal to the negative log of 0.0081, okay, which will give you 2.09. Don't forget, these are the sig figs there. So if you need 2 sig figs, okay, and that should be your pH. Okay, now, what if we're going to do a base problem? Okay, well, you still do the exact same thing. Okay, but the dissociation constant is not called a Ka, it's called a Kb. This is the base dissociation constant. Okay, so, for example, you wanted to find what is the pH of an ammonia solution. Okay, for the base, you have to add water to it, otherwise you won't get OH minus. Okay, so we add water, and notice water is a liquid. So when you write the Kb for it, the water doesn't show up because it's a liquid. So it's the products NH4 plus and OH minus divided by the NH3. Okay, and the Kb for ammonia is 1.8 times 10 to the negative 5th. Okay, so if you wanted to solve for the pH, you wouldn't solve for H plus, you would solve for OH minus instead. Okay, when you do the pH problem. Can't do this problem yet because you don't have that value. Okay, now once you're told what the concentration of the ammonia is, you do the same thing. Okay, OH minus concentration would be equal to X, and that's going to be the same as the NH4 plus concentration. Okay, and the NH3 concentration is the same thing. It's equal to the initial amount minus X, minus the amount that breaks up into OH minus and or NH4 plus. Okay, so here's your practice problem. What's the pH if the ammonia concentration is 0.100 molar? Okay, here's the equation. There's the Kb value. Set it up, solve for X, and don't forget you're solving for pH. When you solve for X, X is going to be solving for OH minus first, so watch out. Okay, it should be one of these. So do your calculation either using the quadratic or successive approximation, okay, and figure out which is the correct value.